All right, let's get right into it. We're tackling two of the most critical topics in your entire AS physics syllabus, waves and superposition. Mastering these isn't just a good idea, it's pretty much your direct path to a top grade. So today, we're going to break down exactly how you can do it. So, why are we zeroing in on this? Well, because waves and superposition consistently make up about 25% of your paper 1 marks. That's a massive chunk, usually sitting right there in questions 21 through 30. The stakes are high, for sure, but the great news is that these questions are surprisingly predictable, if you know what to look for. So here's our game plan. We'll start with the rock-solid fundamentals. Then we'll dive into some of the newer syllabus additions. After that, we'll get into how waves interact, cover some serious exam hacks, and then wrap it all up with a solid strategy. Let's just jump right in with the essentials. First up, the fundamentals. Look, you just can't tackle the tricky questions if you haven't locked in these core definitions from topic 7. Let's make sure these are second nature to you. First, we have displacement. And it's not just distance. You gotta be precise here. That little phrase, in a specified direction, that's where the marks are often won or lost. It's about being a vector. Next up is amplitude. This one's pretty simple. It's just the maximum displacement. So think of it as the peak height of the wave, or how deep the trough goes, all measured from that central equilibrium line. Now for the big three that really describe how a wave moves through space and time. You've got period. That's the time it takes for one full cycle. You've got frequency, how many of those cycles happen every second. And then wavelength. That's the actual physical distance between two identical points on back-to-back waves. Like from one crest to the very next one. And of course, this all comes together in the one, the only fundamental wave equation. Speed equals frequency times wavelength. You are going to be using this formula constantly, so please make sure it's absolutely second nature. Okay, now for a relationship that trips students up all the time. The intensity of a wave isn't just proportional to its amplitude, it's proportional to its amplitude squared. This is, no joke, a massive source of lost marks in exams. So let's test it out with a classic exam question. If you double a wave's amplitude, what actually happens to its intensity? Just take a second and think about that squared relationship. It increases by a factor of 4. Yep, because intensity is proportional to amplitude squared. If you double the amplitude, you're looking at 2 squared, which gives you 4 times the original intensity. Do not fall for that trap. And to wrap up this section, the two main types of waves: transverse, like a light wave, and longitudinal, like a sound wave. Now, what's the one crucial difference you absolutely must remember for your exam? Only transverse waves can be polarized. That simple fact is the key to unlocking multiple questions. Okay, so our foundation is built. Now let's move on to two really key applications that have become super popular in recent exams: polarization and the Doppler effect. And here is another major trap. Malus's law itself is pretty straightforward, but you have to read the question so carefully. If they ask for the new intensity, you use the formula with the cosine squared. But if they ask for the new amplitude, it's just cosine. They look so similar, but they give you totally different answers. This brings us to the Doppler effect. I mean, you've all heard it, right? That change in pitch of an ambulance siren as it screams past you. It's literally just the change in the frequency we observe because of the relative motion between the sound source and us. So this is the formula they give you. Let's just break it down real quick. FO is the observed frequency. That's what you hear. Fs is the source frequency, what the ambulance is actually putting out. V is the speed of the wave itself, usually the speed of sound. And Vs is the speed of the source. Really, the only tricky part is deciding, should I use a plus or a minus? Okay, so here's the crucial part. Think about it. When the source is moving towards you, the waves get all squashed together, right? So you hear a higher frequency. To get a bigger number from the formula, you need a smaller denominator, so you use the minus sign. And when it moves away, the waves stretch out, so you hear a lower frequency. To get that smaller number, you use the plus sign to make the denominator bigger. Simple as that. All right, so we've pretty much mastered how single waves behave. But what happens when they actually meet each other? Well, that brings us right into topic 8, superposition, and how it leads to these things called stationary waves. The one rule that governs all wave interactions is the principle of superposition. And it's actually pretty simple. When waves overlap,
You just add their individual displacements together at every single point to find out what the new combined wave looks like.
Now, there's a really special case of superposition that gives us stationary waves. This only happens under specific conditions. When two identical progressive waves, we're talking same frequency, similar amplitude, are traveling in opposite directions and they interfere with each other. So stationary waves don't even look like they're traveling. Instead, they just have these points of zero amplitude called nodes and points of maximum amplitude called antinodes. And here is a super high-yield tip for your calculations. The distance between any two nodes right next to each other, or any two antinodes, is always exactly half a wavelength. Remember that. Okay, let's get tactical. This section is all about the exam hacks for the two biggest applications of superposition, interference and diffraction. These are going to save you time and lock in those marks. First up, Young's double slit experiment. You know the formula, lambda equals A times X all over D. Here, lambda is the wavelength, A is the separation between the slits, X is the spacing of the bright fringes, and D is the distance to the screen. Let's try a really common multiple choice question. If you just rearrange that formula in your head, you can see that A and X are inversely proportional. So if the slit separation A is doubled, what happens to the fringe width X? It's halved. It has to be. If one goes up, the other has to go down. And knowing these simple relationships means you can answer a whole bunch of multiple choice questions in just a few seconds without doing any real calculation. Next up, the diffraction grating. The formula here is d sine theta equals n lambda. D is the grating spacing, theta is the angle of diffraction, n is the order number, like the first or second bright spot, and lambda, of course, is the wavelength. Now here is a calculation hack that comes up all the time, finding the total number of bright spots, or maxima, that you can see. Step 1, find the maximum possible order, n, by setting sine theta to its max value, which is 1. Step 2, take just the integer part of that number you get. Step 3, double it because you've got spots on both sides of the center. And finally, step 4, add 1 for that big, bright central maximum. 4 simple steps every time. All right, we're in the final section. Let's pull everything we've just covered together into a concrete strategy so you can walk into that exam hall feeling totally confident. Okay, for those cathode ray oscilloscope questions, just remember the basics. The x-axis, the time base, gives you frequency, and the y-axis, the gain, gives you amplitude. But here's the trap. To fit more of a wave on the screen, to see more cycles, you don't decrease the settings, you actually increase them to zoom out. And finally, just remember that these questions are so repetitive. Go through the last few years of past papers, and you are going to see these exact same concepts and traps over and over again. So I'll leave you with a final challenge. Tonight, go and compare the diffraction patterns you get from single-color, monochromatic light versus what you get from white light. Can you clearly explain the key differences? Because being able to answer that shows true understanding, not just memorizing formulas. Master that, and you've really mastered this topic.